Hi everyone, today let's have a look at a couple of by design interpretable machine learning models. The easiest way to ensure interpretability is just to use interpretable algorithms. I mean, you don't always work on the most complex problems, and sometimes, for instance, a simple decision tree can be sufficient. So there's no need to over-engineer the situation. Just like Occam's razor says, the simplest solution is almost always the best. Furthermore, in this video, you will also get familiar with another algorithm that achieves high accuracy while maintaining explainability. If you recall this graph we previously had, we would now be on the bottom right. Of course, we kind of need to ignore the y-axis here, as the accuracy can also be very high or even the highest if the complexity of our data science problem matches the capabilities of our algorithm. More precisely, we will have a look at how to interpret these three algorithms. Decision tree and logistic regression should usually be familiar to you. If not, I will also quickly summarize how the models work. Additionally, we have the Explainable Boosting Machine, or EBM, which is a model developed by Microsoft Research. All of these models are sometimes also called glassbox models, as we can directly look into the model and understand what is going on. So before we get started, let me introduce the dataset we will use for this video series. I decided to choose a health dataset for which the goal is to predict if a person is likely to get a stroke. So it's a classical binary classification problem. I pulled the data from Kaggle, and you can find the link in the video description. In the dataset we have information about several properties such as age, gender, work type, where the people live, and also their body mass index. The target variable is stroke, yes or no. According to the World Health Organization, stroke is the second leading cause of death globally, responsible for approximately 11% of total deaths. Let me introduce John, for whom we will predict if he's likely to get a stroke or not. If he would receive our data-driven prediction, he would be able to decrease the probability of getting a stroke in the future. But also his immediate response would be why after telling him the prediction. And that's exactly where explainability is required. Let's quickly import the data and the code, and we can have a look at all the columns we have available. So this time I'm working in VS Code and not a Jupyter Colab notebook, but I will also push this code to a repository on GitHub. As you can see on the left, we have a data directory which holds in a CSV file the data we have. We have different properties like gender, age, and so on, and in the final column stroke. And the rows are simply our data points. So for all of those we have a stroke yes, I think it's ordered, and then we have stroke no. And next let me quickly introduce the utils file. What I put inside here is a class data loader that simply has a function load dataset, and it loads the dataset from this path which links to the CSV file we just saw. And then it calls pandas read CSV function and stores the data in this member variable in our constructor, so our init function, self.data. Furthermore, this utils file has a couple of additional functions such as preprocessed data, get data split, and so on, but we will look at this in a second. Let's do a quick data exploration, which I will do in this first Python file. And what I use here is VS Code CellMagic, which simply under the hood uses a Jupyter notebook. But we don't have to worry about the notebook, it will all be handled by VS Code. So we can run the cells here, and we can create cells using this prefix. So what I do here now is I import this data loader from our utils file, and I initialize it, load the data set, and then assign the data set of this data loader to a local variable called data. So let's run those two cells. Okay, now we can have a look at the data. So let's print the shape. We see we have 5,000 data points, and if we print the head, we see we have, so the first 5 data points, we have those columns here: hypertension, heart disease, so it's binary yes or no, married, work type, different kinds of things. We can also run this data.info, which gives us basic information. We see we have a couple of object columns, which basically refers to categorical or non-continuous columns. And furthermore, we have also things like ID, which we probably won't need. Also the body mass index, which is a float value. Next, we can iterate over all columns and then simply print a histogram for each of those columns. So let's run this. And now what we can see is, okay, ID is not important, but for gender, for instance, we have more females than males. We have an age distribution, which looks like this. Hypertension, only a couple of people have hypertension. Let's say 500 of our 5,000, so 10% maybe. Same for heart disease. Most of the people are married. We also have different work types like private, self-employed, government job with children, I guess, I don't know, and never worked. And other things, so it's not too important, to be honest, for the things we want to do. And that's the most important thing, our target variable. And as you can see, it's quite imbalanced. We have only, let's say, 300 patients with a stroke in our dataset and the rest without. Next, we can run the preprocess function, which, let's quickly have a look at it, does the following. It gets the one-hot encodings, which we can do with this pandas dummies function, and for all of those categorical columns. Further, it appends them to the original data and drops the old categorical columns, so those. We can quickly have a look at this. If we run this function, we see we get things like gender female, gender male, gender other. So instead of this column gender, we have now 3 columns which are 0 or 1 for each row. So this row would be a male, this row would be a female, and so on. Then another thing, we saw that in that info plots here, we have missing values for body mass index, and I simply impute them with 0. So there would be more intelligent strategies, but we will do it like this for now. And finally, I said ID is not important for our prediction, so I will drop ID. And usually you should always standardize the data to enable better learning for the algorithms. But here, as we want to interpret a couple of values, we would need to convert them back basically. And to avoid this, I will simply ignore the standardization. Okay, so now that we are familiar with the data set, let's quickly have a look at the first algorithm, logistic regression. Logistic regression is an extension of linear regression to classification problems. Using the sigmoid function displayed here on the right, the output of the linear regression is squeezed between 0 and 1. That means we get probabilities. Using these probabilities, we can, for a binary classification, assign the class 0 or 1 depending on the output value. So under the hood, we use the same concept here as for linear regression, and that means we get the output as a weighted sum of input variables. And these betas here are learned during the optimization of our model, which simply means we adjust them to minimize the loss function. Now back to explainability. It is straightforward to interpret the coefficients here that led to our prediction. For the classical linear regression, if x1, for instance, is a continuous feature, such as h, increasing that x1 by 1 unit will make the output y increase by beta 1. This way we immediately understand the impact to our output y of a change in the input features. In other words, we have full transparency on how the prediction is calculated and also know the contribution of each input to the output. For logistic regression, we need to consider the sigmoid transformation we apply. After a couple of equation reshapes not displayed in detail here, we get this, and that simply means if x1 increases by 1 unit, our outputs will increase by e to the power of beta 1 units. Okay, so now let's have a look at our dataset and see how this works in practice. We will use a Microsoft library called Interpret, which contains most of the algorithms we will capture in this XAI series. Okay, so let's have a look at this first file, interpretable models, for this first video. Here we simply again import our data loader we also used in the data exploration, and additionally we import the modules from this interpret library. So all of those are glassbox algorithms, which simply means transparent by design interpretable algorithms. Furthermore, we also import this show function which generates an interactive window, and additionally a couple of metrics from scikit-learn, such as the F1 score and the accuracy score. So just like before, we now load the data set with this data loader and pre-process it. And then I call this getDataSplit function, which simply returns this test train split for 20% test data. And additionally, to mitigate the impact of our class imbalance, I apply this oversampling function, and there I use a random oversampler. What that means is for our minority class, we simply sample more data points to get a larger distribution, which means our learning algorithm sees more of those data points in the train data. So that means as input, we get the original train data, do this oversampling, and then return the oversampled population. That's why our data set also increases, but again, I only do this for the train data. Okay, so back in our interpretable models file, let's run those first two cells. So the imports and this data preprocessing. And you see previously our train data was around 4,000 data points. Now we have almost doubled it. So next we will use this logistic regression model, and that comes from this interpret.classbox package. And under the hood, this simply uses the scikit-learn model, but additionally we can call additional functions such as explain local and so on. We will see this in a second. So now let's first train it, calling the fit function. We simply pass it the train data and the train labels. Okay, training finished, and now we can perform predictions and evaluate them using the F1 score, which is important because we have an imbalanced data set, and just looking at accuracy would not be enough information. For instance, we could always predict no stroke and would already get a pretty high accuracy. And the F1 score is the weighted average of precision and recall and tells us more about how also the minority class is predicted. And we see we get an accuracy of 73% and an F1 score of 51. So now what we can do is we call this logistic regression explain local function, and we do this for the first 100 data points. And simply what this does is explain individual predictions, and that means for the first 100 data points. And here in this interactive summary, let me enlarge this, we see different data points, and if we click on this, we get explanations which refer to the coefficients in the linear or logistic regression problem. And here, for instance, the age has a strongly positive impact, and things like if the person was married, which is 1 in this case, or the fact that this person never smoked, reduces the stroke risk, basically. But what we can also do is we can interpret global predictions, or not global predictions, but rather global features. And here this way we can see the overall importance coefficients. So that's basically for all predictions. So as we've seen, the interpretation of the coefficients is straightforward, and therefore our test patient John approves this by design interpretable model. For completeness, I want to say that in case of correlations between the inputs, the interpretation of the weights might not be reasonable sometimes. But if you're interested in more details, read the book I've linked in the video description. Next on our list we have the decision tree, which is another algorithm that is commonly used. Important, that doesn't include ensemble methods like random forest, but just a plain original decision tree. The big advantage is that these trees are able to model nonlinear relationships. The way how it works is that they grow a tree, such as the one displayed here, by applying feature splits that are able to separate the data. On the leaves of the tree, we obtain the predictions, such as here, stroke or no stroke. There are different ways how to grow a tree, and I just quickly explain the ID3 tree generation algorithm here. The way how these feature splits are selected is based on a concept from information theory called entropy. A feature that is able to split all of our data into two classes, stroke and no stroke, has an entropy of 0 and therefore the highest information gain. On the other hand, if we are not able to correctly separate all of our data into the two buckets, we have some impurities for that split, which are expressed by the entropy. So we can calculate the information gain by splitting each feature and simply select the best splits. Interpreting decision tree works by starting at the root node and then simply following the edges to the leaves of the tree. In this example on the right, for John, we would check his age, he's older than 50, and then his body mass index, which is 23, and we end up with a prediction for no stroke. That means a decision tree can be interpreted as a set of if-else rules, which are human-friendly explanations. Furthermore, we are also able to read the feature importance from the grown tree, as we know which features led to better splits than others. Finally, a decision tree allows us to transparently follow the reasoning process, and we can, for instance, say, if the body mass index of John was higher, he would be more likely to get a stroke. Now let's quickly implement this for our dataset. So here back in VS Code, we use this classification tree, which comes again from this interpret class box. So it's that second import here. And we fit it using the fit function. And again, we predict on our test data. And that was pretty quick. We see we have an accuracy of 73 and an F1 score of 0.52. So if we call this explain local function again from interpret, we can even get the graph here. And the graph shows us with the red line which path our prediction followed. And here, for instance, we have age smaller than 56.5, and here it was a subject with age higher than that, so that's why we go the red path. Another important thing for decision trees is the depth. So here we have 1, 2, 3 decisions we have to make until we end up with a prediction. If that tree has, for instance, 500 decisions we need to make, it's getting pretty complex. So decision trees are only interpretable if the depth is reasonable. So after our prediction for John, he said, okay, those rule sets totally make sense for me. That's why he approves it again. So now let's talk about the last by design interpretable model on our list. Explainable boosting machines were developed by Microsoft Research, and their goal was to mitigate the trade-off between interpretability and accuracy. So if we think about the graph we've seen before, EBMs would be on the top right, like this. They built several decision trees where each of them is only allowed to use one specific feature. They do this in many iterations, such as 10,000, and then they summarize all the results of the fitted trees for each feature. What they end up with is a graph, like the one shown here, that shows the impact of a feature on the target variable. This is some sort of dependence plot. Such visual explanations are easy to understand for humans, and we can directly see why certain predictions are made. If you're interested in further details, there's also a video on EBMs uploaded by Microsoft on YouTube. I will link it in the video description. Okay, so now let's apply EBM on our dataset. So again, we initialize this EBM model, and now we train it just like the other models using our train data. And what we can see, it takes a little bit longer because, as I said, it needs to fit several thousand decision trees. And then the prediction we get is this F1 score of 0.55, so we got better here, and an accuracy of 87. So that's much better than the previous ones. And we see, okay, we got a better performance, but as we will see now, we maintain the interpretability. So if I run this explain local cell again, we can have a look at the explainability of this model. So again, for individual predictions, let's say for this one, we see the impact of specific numbers. For example, here we had a age of 8, and that's why the prediction was rather 0 than 1. Okay, here we see that the age is relatively high, which would mean we have a stroke, but there are other things like the relatively normal body mass index that shift the prediction to the left. So we get that kind of explanation for each individual prediction. And again, we can also do this globally. So let's run this cell. And we see we get this feature importance plot, and it says the most important feature by far is the age. And then it's the body mass index and the glucose level. And after that, it's combinations of specific features. So now one last thing we can do here is also investigate individual features. Let's quickly search for the most important one, which is age. Here we can see that the impact of age is for here -5, so the second term in this tuple. And the higher the age gets, so here we have 80, the more likely it is that we have a positive impact, which means we shift more towards stroke instead of no stroke. For example, here we have around 3. So you see we have a positive trend here, and that's the plot I've also shown previously. So we can investigate the impact, so basically the dependence of features to the target variable. So for EBMs, we could prove on our dataset that the accuracy and the F1 score get better, while the explainability remains. That's pretty cool, and therefore John, of course, also approves this method. That's it for today. As you've seen in some cases, we can also get decent results with by design interpretable models. However, sometimes neural networks or random forests work even better on data, and that's why we focus on those black box algorithms in the next videos. So I hope you enjoyed the series so far, and I see you in the next video.